Okay, to people joining this live stream, this is part of our cycle of design reviews for version 13.1 of Wolfram Language. And this afternoon, whatever it is, we are looking at control and system modeling. So where should I look at these things?
These things are source pages, reference pages.
Can I run them in a build?
Yeah, if you have
next kernel.
Yeah,
the prototype build.
Okay. Somebody check that I have a current prototype build. Let's see. Just check that. I hope I do. April 20th. Is that the right time frame?
Yes, so things should work. Maybe you don't have all the latest, maybe one or two little properties may throw an error, but
okay. All right. Model predictive controller. You know, one of these days we should figure out how to make these things actual internal links so I don't have to retype the name every time.
You can, if you click that dot, when you highlight that thing in my notebook.
I know. Oh, when I highlight it. Oh, and then I click the dot. Oh, okay, that works.
Yes.
All right. What is this creature?
Right. Okay, so let me give you the backdrop and then explain what this creature does. So one way to design a controller is to basically optimize for, you know,
Sorry, where are the examples? Sorry, where are the examples?
They're closed. The cell is closed, apparently.
Oh my gosh. You know, every function where you don't get to the function for, you know, like 8 inputs is a function that scares me.
Yeah. So can I explain, or do you?
Yeah, please go ahead.
Okay. So one way to do that is to sort of optimize for, let's say that your goal is to drive the signal to 0, you know, or some constant value. So you want to do that, but use as little control effort as possible, because control effort costs money, basically.
Okay.
And you know, and you can take into account sort of unknowns, otherwise known as noise, of what can happen. But if you do that, so people have done that for very slow processes. They literally run an optimization process that looks what's going to happen many steps into the future, like that. They literally run an optimization routine that does that.
Okay, so just I'm lost here. So
yeah.
We've got, this is a typical control system loop. Is that a true statement?
Yeah, it's a system that has some kind of internal state that you have, you know.
Yeah, but I understand that. But how contrast this with what's its of the functions that we already have?
Which is basically, this is kind of like, this is a more sophisticated control design than the functions that we have for control design. And so this one can take into account variations that happen. It can take into account constraints, because in real life, you know, systems are not linear. Like if you have a plane, for instance, the control surfaces can only go so far, and then they hit the limit.
Yeah.
Okay, so all kinds of real world systems.
This is so complicated. I mean, you know, my question is really this. There are experts in this kind of thing who presumably will understand what all of this is, and hopefully will use this.
Well, I think that this can go perfectly well into courses and you know, kids to take their first control class and stuff at this point.
Where I don't understand what. Okay, give me a scenario where you know, let me have a scenario that is even vaguely a me type scenario. So I'm not controlling a plane. I'm you know, I'm trying to I don't know. I mean, what's an example where this is realistically something that I could use as part of some workflow that I'm actually doing?
Well, I don't think you've ever designed a controller, but
I thought about it a few times, and it got so complicated I gave up.
Well, yeah, because you kind of validate it and make sure it actually really works and stuff like that.
Well, okay, so I mean, let's be very basic. Okay, the one that I was going to do just for fun was control an HVAC system through a Raspberry Pi, through with but I mean that was going to be some trivial PID controller like thing or something.
Yeah, and so no, you can do that. HVAC system is a perfectly good example of that. There's only so much you can do. I mean, the control signals is limited even in an HVAC signal system.
Well, okay, so I mean, you've got a thermometer, and you've got and you've got a thing that can blow hot or cold.
Yeah, and there's a maximum level it can blow.
Right.
And you probably can't go negative.
Yes, but okay, so I mean, is this, if I were going to do that in a very fancy way, using maybe extra signals like, the temperature outside or who knows what else, could I use this? And walk me through how I would use this. I mean, what is the basic structure of the code that I would write for the HVAC system?
So whenever you do, and this goes for almost all of our control designs, which is that you need a mathematical model of the thing that you're going to control.
How about if I don't have it? How about if I'm absolutely clueless? I don't know how, so I blow hot air into the room. I don't know how quickly it heats up.
Right. And so then what people usually use is kind of a very approximate model. You might just do, like a spectral model, like you basically get a transfer function or approximate transfer function, or you try to do it model-less, which means that you kind of tweak parameters on a PID. If you know nothing about your system, then there's probably no point in trying to use anything more sophisticated. Then I think it's better to use something more generic, like an auto-tuning PID, like we have.
Okay. So how would I do that? What's the function?
PID tune.
Okay, but I mean, okay, but so if I want to write the whole loop, in other words, I've got.
So once you get the controller,
I get the controller. Is the controller a function, or is the controller what is the controller?
The controller is a dynamic system that needs to be implemented. And
no, so but I mean, but I mean, the controller is basically, it takes in values from the thermometers or whatever, and it puts out signals to the heater or whatever.
Yes.
Okay, and that is typically encapsulated in one of these kinds of transfer function models. Is that correct?
Yes.
But then where do I put in? I mean, S isn't I mean, this is a representation of the model, but how do I feed in the value of the temperature?
Well, that's the input to that. This if you click on the details and notes, you can see where all the signals are, and you can get exactly the thing that you want.
But naively, okay, so let's just say that.
So the temperature is Y here. Okay, that's the thing that you measure.
Okay. But so just so I understand the workflow here, in the end, let's say you're doing it purely through Wolfram language, where you're not Arduino-ifying it or anything like that.
Yeah.
Then let's say, every 5 seconds, let's say, you sample with device, with our device read or whatever, you sample the value of the temperature. Okay. Then you and I feed it in somehow. How do I store? This thing has to know, presumably, the time history of those values. Is that not correct?
Yeah. Yes, but it needs to not know the full history. It just needs to know as many states as you have. Like, so if you have 2 states, it needs to know 2
Hey,
senses.
but I'm
back.
trying to be very practical. I've got this Raspberry Pi thing.
Mhm.
It's been measuring it every 5 seconds. It samples a value of temperature.
Yeah.
Okay, what do I do with those temperatures?
You need to sort of remember them.
Okay,
And
I do that in our system. How should I do that? How should I actually do it? So
I mean, if you
into,
build the implement, I mean,
Yeah.
so the the thing that generates code, which is our sort of microcontroller kit, it takes care of sampling them and all of that. But if you have the thing that you looked at has S there, it's what's called continuous time. So that's a differential equation. So you need to discretize it. First step. But then you have basically, you can read off the difference equations that you need to run, the recursion that you need to run.
So I'm already totally lost. So, I mean, I understand that one approach is you make an Arduino and it is
But Arduino is like, has almost nothing to do with it. You could run it on whatever you want.
Okay, but how do we do that? I mean, you got to take in.
We've automated those steps that I just described to you.
Okay, so then tell me what piece of code do I run on the Raspberry Pi?
The code that's generated by, what's it called? The deployment function.
Microcontroller embed code. But just to step in, so if like as Stephen is saying, you just want to do it in Mathematica instead of doing it on an external device.
That's what I want to know.
Yeah,
that's what I want to know. How do you do that?
So you take that. Yeah, so from PID tune or microcontroller or any of these controller functions, you get that transfer function, which is the controller representation. Yes. And you're going to do 2 discrete time model that will give you the discrete version of that controller. And then you're getting these signals from, collecting these signals through device read. Now, those signals are going to be the input to this controller. So you'll use output response to get the response from the controller. And you'll take those signals and feed it back into the system you're controlling.
Lovely. How do I actually do it? What do I do? Do I append values to some list and feed them into the control function, or what do I actually do?
Yeah, the device read functions, those values, you take a window of
that. No, but you don't take a window because they don't have a way to take a window. They just take values, right? So what is our wrapper? What is our way to actually do this? Right, this gives you, if I'm not mistaken, this just gives you a value.
Value, yeah.
Right, so what exactly do you actually do?
So that value is the input to the function output.
I'm aware, but you've told me I need multiple such values. How do I keep the, I have to, and
you have to keep a cyclic list basically of how, let's
so
say you need
you
to
have
keep
to do
3.
that. You're on your own. We don't help you with that. Is that correct? We don't have a function that does this. Yeah, I have to build it myself.
Yeah, because we don't think about implementing it in the Wolfram environment itself. We think about deploying it to an external, because controllers are typically deployed.
Okay, but you just told me that this is doing an optimization loop. So that's not something which is going to be deployed to an Arduino, is it?
You interrupted me before I could finish.
Yeah, I know I did.
Okay, but this if I can't finish telling you, then I won't tell you.
Okay, go ahead, Roger. Go ahead. But I mean, I'm trying to understand what this is. I mean, okay, here's my point of view about this. Okay, maybe this Arduino thing, we have a deployment mechanism, but this is so freaking complicated. I mean, whatever. I can't believe it needs to be this complicated. But go ahead, go on. I'm listening. Tell me how this works.
Well, if you run an optimization program, each sample, it needs to be a very slow process. So maybe your air conditioning system is slow enough.
Yeah.
Chemical factors were slow enough.
Mm-hmm.
In order to run it fast, you want to pre-compute it. So you don't have to run an optimization program in the middle of doing this. Mm-hmm. And this is what this one does. This is what's called explicit model predictive control. So this will actually generate something that can run very fast, that can be, also deployed on microcontrollers and other things. And so this is what this one allows you to do, this more sophisticated control design that takes limitations into account and computes beforehand, so they can run on even fast processes, like motion control needs to be fast, for instance.
Yeah, so the workflow is just like PID tune. So from PID tune, we get a transfer function, which we have to deploy or use it, as I said, in the Wolfram language. This one
will have the
returns.
same workflow.
Yeah, this
You
one
know,
returns.
you do a design, something comes out, that's what you're going to deploy.
And here we're just simulating it, the closed loop system, just we're doing verification.
So where's the example that shows deployment?
There's no deployment here.
Okay, but you will include an example of that, right?
Yeah, we can do that. Actually, the microcontroller deployment will be for 13.2. We don't have that for 13.1. This is more sophisticated, so it takes a little, you know, takes more effort to generate those.
Okay, so I mean, this function clearly has, you know, it's just pages of stuff, right? Clearly, it needs many, 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 many more examples than this.
Yeah, it's in the scope. Yeah, it's not yet complete, but there are examples in the scope and so on. Yeah.
Okay, I see that.
But it's not yet finished. But
okay,
I'm working
fair
through.
enough. Fair enough. But so, okay.
So this is part of the sort of hot sort of control technology that people expect to have. And I've been asking for that matter. And I think that the biggest advantage, as I said, it can take constraints into account when you do the design.
Okay.
And this thing of making an explicit one, it's as I said, the biggest advantage is that can run fast processes. If that needs to run in milliseconds or microseconds, it can, not a problem. The other thing needs minutes.
I can't really help with this design because this is, you know, deep inside an area that I know little about. And this is an unbelievably complicated thing. So I don't know how to, you know, I don't really have much to say. I mean, I don't know what, I mean, you've got a cost function that apparently has, I'm sure there are different norms for applying the cost function. I mean, I guess my only question would be, you know, we have a certain framework for sort of representing things in machine learning and reinforcement learning and so on. And this is a completely different prong, a completely different community that does control system stuff. And we haven't really done much to bring these two together. And maybe there's nothing we should do because it's incomprehensible to people. You know, maybe it is the case that you have to dive this deep to be able to get anything to work. In which case, it's really hard for me to review this because I don't know what yeah, I mean, you know, you've got, go ahead.
So when you're doing reinforcement learning, so in that illustration that you see above, right?
Yes.
We have, so this page shows how to compute that, what you see in that green box, regulator.
Yep.
So in reinforcement learning, there's another, it's just another algorithm to compute that regulator in a different, it'll be a different regulator, but a different way and a different.
Okay, but is the framework the same?
Yes.
Yeah.
But so we can use, you know, transfer functions and all that kind of thing in reinforcement learning. Is that correct?
Yes, we can. Yeah.
So the same framework. So I can have, instead of saying model predictive controller, I could say reinforcement learning system and the same S-spec cost and constraints. Is that correct? I could, it's plug compatible. I mean, it's just a different algorithm.
No, we don't have reinforcement learning.
No, I understand.
But the principle is the same.
Okay, but so assume we were going to make this into, I mean, you know, is this, other than the fact that this doesn't happen to use neural nets and so on, is the workflow of this the same as reinforcement learning?
It could be if you have a model of the environment, they call it an environment there.
Yes.
Then you can operate on it. And now, because you can't really, and we need that. That's a way to make reinforcement learning work, is to have environments that you can operate on.
But I mean, well, wait a second. I mean, in our existing reinforcement learning stuff, we've got things like the sort of models of video games and things like this.
So that's a family of environments which you can operate on. Yes.
Yes. Okay.
Right.
So,
but these mathematical systems would be another family of environments that you could operate on.
But so what we've talked about before is what the API for those environments is and how it plugs into the, this overall.
No, I mean, reinforcement learning is going to want its own converters to set up that the environment behaves like their formalism wanted to behave.
Okay,
so they're going to mess around with it a bit to get it to fit that framework.
Right. But so what I'm asking is all these lines here, okay? So, the thing we understand from our language in general is there's a function, it's applied to arguments, it does its thing. And those arguments are always represented as symbolic expressions, and we kind of understand what the overall workflow of f of g of x is. Okay, what you've got here is a different kind of workflow.
These are signals. These are functions over time.
Yes, I know, I understand that. But so what you're defining here is, essentially a dynamic analog of sort of function application, which is not function application anymore because it has this dynamic loop, right? So what I'm trying to understand is what is the general thing that is that dynamic loop function evaluation kind of thing? And isn't that the same kind of thing between, in particular, reinforcement learning and control systems and probably other things too?
Yes.
And so what I'm trying to understand is, what you've got here is a very specific, thing for specifically for control systems built out in control systems lingo, et cetera, et cetera, et cetera. I'm trying to understand.
Control systems is a generic technology. It applies to a wide variety of fields.
Okay. But I want to know.
So it's not that specific.
I understand that. Let me just remind you, just design-wise, when we were first building Manipulate, okay, that thing was unbelievably complicated. It was full of pseudo variables and this and that and the other, and it's just really messy. It took a whole bunch of grinding, and eventually we have something which is very easy for people to understand. My question is, and I've asked this before in these meetings about control systems, I'm pretty sure that there's a similarly easy to understand thing. I don't understand it, but there's a, let me give an example. The thing we talked about machine learning. Could we make a generic wrapper that says, learn this function, that wraps around functions?
I think Jerome has recently had a prototype of this where he took an inverted pendulum and solved this problem. And instead of regulator, he has a reinforcement learning controller. I hadn't seen the results of that, but.
Okay, but that's fine. But what I'm asking is not what the internal subroutines are. I'm asking, what is the top level design that represents this control loop, basically? Do you see what I'm saying? Because that's the part that I think if we can get a really clean way to do that, that's, and it is a different thing because it is something which, like Manipulate is a different workflow from our usual, you give input, you get output, right? Similarly, this is a different workflow from that.
Yeah, but most of the controllers won't live in Mathematica. That's like almost no point in having them live in Mathematica.
I understand that. I don't care. The thing is to get something. I mean, just like you could say a function f, I want to compile it. Okay, it's now compiled. Now it runs in, in machine code, but it's still the function f, which I could call in top level, Wolfram language code, right? It doesn't change its workflow. Now, if you tell me that this needs to, and yes, the function f may have a different externalized workflow than it has as an internal workflow. That's an issue for it. But in this case, if what you're saying is this loop, all you're trying to do is produce Arduino code, basically. And this is essentially a symbolic specification.
No, we do put them together in the, you put them together inside Mathematica as well and simulate them together because you want to test things before you go, so to speak. So you do put them together. You run simulations inside Mathematica. Absolutely.
Okay, but then what I keep on saying, it's the same thing, is what you've got here is just a function which, tells jokes by numbers, so to speak. You have to know this whole elaborate thing. Look at
I'm explaining it. That's why it's so long.
I understand, but look at all the structure you have to build up to be able to use this function.
Yeah, but if you're going to even specify an optimization problem, you specify as much, right? Or differential equation, you specify as much, for sure, at least.
Okay, but like this, for example.
Yeah.
that's some whole complicated, that initial, what is that initial sequence there? That thing, that thing there, that is some kind of order of the state space model. Is that correct?
Yeah,
that's a difference equation. Bunch of difference equations.
Okay, how would I have the slightest idea what to put there?
Well, there are many ways to get to that. You can linearize, if you have another model, you can linearize it and get to that. But yes, that's very hard to get to. This is what we have addressed previously. We've linked it up with System Modeler, that you can use those models of things.
Okay, but so just to understand, if I change that 1 to a 2,
yeah, I've completely changed the plant.
I understand.
The environment.
I understand. Yeah. I understand. But how would I know? I'm just coming in off the street. How would I know that I want list 1101,
Well, that's the parameterization of state space model. You have to look at the function. They take parameters, right? And this guy takes matrices as parameters.
Okay, but so roughly, do I know this because I took a course in control systems?
Yes.
And they told me,
or in the future, that page here, I don't know, I don't trust these pages yet until we've worked them over to become learning pages. Otherwise, you could just read this page. In principle, it's there, but it might be a little fast.
See, I don't understand this. Write out, okay, you're not explaining, you're just giving this weird thing here. And there's just no explanation. Okay, let's see if I can understand it. A, B, C, D. State matrix this.
I think in the third cell explains what ABCD. I think so. The third.
This one here?
Yeah.
Continuous time system modeled by the equations. This thing, this thing, this thing.
And the next line is for a discrete system.
Okay, so there are random coefficients in that equation.
I mean, random wouldn't be a good model.
No, I understand, but they're coefficients. Whatever.
Yeah, modeling is hard. We need to become better at it.
Yeah, what I've been pushing to get something
just what I was saying, like, let's say differential equations. How the fuck do you come up with the differential equations? And what we automate is desolve and desolve, but it assumes that you can come up with a differential equation.
That we have these kinds of named, which we finally have, that we have for PDEs, at least we're starting to have named, PDE.
Yeah, we're building that, but those named, I mean, the domains, I think, is very useful. The named PDEs, not so useful, I think.
Really?
Yeah.
Why can't okay, if I know that I want an integrator, what is my workflow for getting this? Can I go through System Modeler to get, is there an entity that represents an integrator? That's a system model of an integrator.
Yeah,
that I could like not yet, but eventually say control equals integrator, and I could get that integrator model, which I could then feed into the, either use as the state space model or feed into the state space model.
Right. So in our modelica libraries, we have a component for integrator, and then you can linearize it and obtain a space model.
Okay, but what I need to be able to do is to go and type, control equals integrator. Okay, we need to have linguistics so that I can actually get to that system model that way. Am I making sense? Because that's otherwise you're asking me, otherwise I'm diving into some giant, browser adventure, which is a completely different kind of approach to doing things. Right? How would I find the integrator?
Right. So you could write a system model and then integrator as a string.
Really? How would I know that?
And then it's possible that you're going to get several matches because we have several components for integrator. But then you can just pick one of them.
Okay, but so what you need to do is integrate it with the natural language stuff. If you've got a way to search for this, we've got to figure out how to integrate that with our entities and so on. Am I making sense?
Mm-hmm.
Oh, that's hopeless.
Yeah,
I mean, it's hopeless. Hopeless.
It's because you get several.
I know, but that's no good. We've already got a framework for dealing with multiple matches, and it's not this, but you're not using it. Right? This is what I've been saying for years. Right? You've got to actually use the framework that we have. So you're saying op-amps dot integrator. Well, where is the generic integrator?
I think it's the first one.
That one there.
Mm-hmm.
Okay. Now, how do I get a state space model from that?
You do system model linearize of that.
Okay, I lose. Explain.
That error message doesn't make sense.
No, this is the thing that we've been seeing for some time, that when there are
But it's wrong. It's not right. I mean, this says continuous integrator, right up there.
Oh yeah.
So this, there's something wrong.
Hey, this is no good, guys. This is like, you got to actually think how people will actually use this stuff, right? It's one thing to, to get something which works in a textbook. It's another thing to actually build something people can use. And, this is kind of comedic. Come on, we can do better than this. We've got a whole giant framework for dealing with entities, dealing with things like this, that doesn't involve some crazy error message when we got multiple matches. Am I making sense?
Right.
And, this is fine. If I can get, from integrator, I get the system model, that's beautiful, right? It doesn't work right now, but if it did work, and then, to say, okay, you linearize that system model, fine, all good. What would you have expected to get out of that? An actual state space model?
Yes.
Okay, fine. So that's great. That seems like a great workflow. And it's impressive we have all the components necessary to build it. Now let's actually build the workflow to make that work. Okay, so then I'm going to get that system model. So I'm not typing this weird thing here. And I don't have to say sampling period, which who knows where I know, what the sampling period is supposed to be.
I mean, that's what your system is sampled at.
I understand what it is, but I'm just asking, how do I know if I'm trying to model my HVAC system, for example, and all I know is I've got a thermometer, I've got a thing I can change the temperature of. Those are my two things I can control. And and I didn't take a control systems class. Do I have any hope of using our stuff, or is it hopeless? Do I have to dive into, state space models of this and that and the other of LQ something or other things, and that's like hopeless. We can't, not end user usable.
No, I don't think that the pages are written for someone that haven't taken a class at this point. They're not learning pages.
Okay.
The functionality is not designed. You need basically an intro class to control.
Okay, well, fine. So I mean, it's like
but it's like 101. It's the thing you take in sort of year 2 or something like that.
Right, but if you're doing linear algebra and you're diving into QR decomposition, that's not going to be done by the person who just knows what a matrix is. That's going to be done by somebody who's taken a numerical analysis class.
Yeah, but even linear algebra, you probably need to have a class on that.
Well, I understand, but if there are people who will use, basic things with matrices, okay, you're right that all these things need some amount of understanding.
I mean, it's coming in earlier and earlier in that case, for sure.
Right, but so I mean, what I'm asking is, can we take all this stuff and make it so that there is a flow where there is a reasonable chance that somebody who doesn't have to
there is a pretty good flow. I mean, okay, Stephen, there is, but these pages haven't been rewritten to be sort of learning pages and basically do the course for you.
Okay.
But the flow, in the terms of the flow that we have, it's not bad. It's
Look, I'm looking at this. I can see what it is, right? It's kind of complicated. Now, maybe you're telling me it has to be complicated. Maybe you're telling me there is no model. I mean, it's just like, in recent times I've been re-looking at all these mathematical logic things. Okay. I could take what we do in pattern matching, transformation rules for symbolic expressions, things like that. I could write that in mathematical logic ease. Okay, nobody would ever understand it, or almost nobody. 6 people on the planet who are experts in those things would understand it. It will be unusable.
Mm-hmm.
But the fact is, if you look at like you can describe the way we do pattern matching, for example, you can describe that in terms of all kinds of concepts in mathematical logic and so on. Sure. And you can define the fact, we've got an operator and a variable and a this and a that and the other thing. We've got 17 differently named things. Turns out they're all just represented by X blank. Okay, but it takes effort to turn it into something where you're just representing it in terms of X blank instead of just copying the textbook. And what I'm suspicious about, but I don't know this field, so I can't really tell, I'm suspicious that we're in the copying the textbook phase. We're not in the grinding this down to the point where we're actually getting the essential things that we can do, given that we have, symbolic representation of arbitrary expressions, et cetera, et cetera, et cetera. That's my point and my objection here. Am I making sense? I mean, I can't do it because I don't know this field. And
yeah,
but
what we haven't done right now, Stephen, is to throw away all the work that was done before, right? The years of work that put into control system before and start over and say, we're going to design a new way of thinking about control systems that nobody has ever heard of. We have not done that.
No, I know. It's the same thing it's the same reason. If we provided a system that used mathematical logic, it just said, we're going to go full mathematical logic. We're going to have De Broglie indices. We're going to have,
I'm familiar with it. It's sure,
right,
sure.
Right. We're going to do, you don't think we're going to have a function. We're going to have eta reduction instead.
Yeah.
We're going to have
nobody studies that logic at the elementary level. This control systems is basically elementary courses. This is different,
Well, okay. So that you're saying that, okay.
This is broadly applied. This is broadly used and taught.
Okay, well, I'm just not in its target market, so I can't.
No, right.
Right. So I mean, that's and nor would I be in the target market for eta reduction.
Right.
But I am in the target market.
But see, eta, that stuff, that's like one of those classes with 4 students in it.
Yes.
It's a very different niche. That's what I'm saying. Like. People come to us and ask for things sometimes, which you could say that it's like irrelevant. Like think about all those named hypothesis tests.
Sure.
That's kind of silly.
Okay. So I hate those things, but I will say the following. Yeah, I know. I will say the following thing about them. They are cognitively straightforward. That is, once you know what a hypothesis test is, having Joe's hypothesis test and Bill's hypothesis test is not cognitively, it's just like saying, once you have the concept of an entity that represents a chemical, you might as well have 20 million of them, so to speak. The difficulty here is that there's a lot of structure that you have to,
it's similar in all the design functions. It's similar. It's the same structure.
Okay, well, that's helpful. The thing is, part of what's difficult for me, okay, so like, I just don't know how to start here.
Yeah, I don't think that that's super easy. That's why we put effort into building bridges to, we have the best modeling system in the world, for God's sake.
Yeah.
System modeler is the best in the world.
I understand.
So we wanted to use it, and we are.
That's right. So that's why I'm saying this workflow, and I think this will be great. Okay, if we can smooth this workflow, this will be great. But we tripped twice here.
Well,
makes sense. This needs to work. If we make this workflow work, it will be great.
Okay.
And this thing is just a bug.
Yes.
So, in any case, okay, let's go back to this. We're going to run out of time. So let's go back to looking at this. I mean, I'm not sure that I can help you very much on this. This is
no, I understand that. It's sort of just that the workflow is exactly the sort of outside workflow. You have a model, you can give sort of design specs, which are goals, and you can give constraints. You let the algorithm churn and it will compute you and will give you an optimal controller.
Right.
The way that interacts with the system is exactly the same way that all the other controllers interact with your system.
So the thing is going to generate I can't see it. Okay, system connections model. Systems connections model.
No, it's the one above that is generated. So all our controllers now generate
controller data.
Yeah. And that from that, this is what we automated. So you can get all these things in one. Yeah, putting those like closed loop system. If somebody had to manually do that, that's
you guys are so close to having something really nice. I just think there's more to understand about how to do this. You know, maybe not. I don't know. Maybe there's no choice.
I'm not saying you're wrong, Stephen. I'm just saying that we didn't design something odd and we didn't throw away what we have.
No, I understand that.
We didn't design something odd that people don't recognize. This is one step forward to say this is not standing still. This is the modern control systems. This is what people have been asking to be able to use.
Why do we need to do something like this? Evaluate list data at.
Yeah, because it's hold also. Otherwise, it won't just return an empty plot.
No, we need to discuss that. We need to discuss that. We need to discuss that mechanism. I don't think that mechanism is right. It's a much bigger issue that has whatever. All right. Well, so what is the comparable to this function? What is the other thing that you can use? You know, is there a plug compatible thing that doesn't contain those constraints? Is that right or not? What is it?
Yeah, the younger brother of this is LQ regulator gains. LQ regulator gains is almost the same, except that it doesn't have constraints.
Why does it have a name that has nothing to do with the name of this function?
Which one?
Well, it's called LQ regulator gains. Why is it called such and such controller?
I think we should rename them controller, to be honest. That's the more correct name. That was an old name that you guys decided on a long time ago.
Who's the you guys?
You and Peter Overman.
My God. Okay. Well, it seems wrong. I mean, if it's in a family of controllers, why on earth is it called this?
We're planning to actually rename all this to controller.
So what will it be called later? What will it be called in the future?
LQR.
LQ controller, yeah.
Or LQ controller.
Okay. And so then it will take, it's right now I'm seeing spec, cost, constraints.
Yeah, this will take spec and cost. Yeah, weights, yeah, this is the same thing. We just use different symbols. Weights and cost are the same.
Okay. Okay, so this diagram
is the same.
The same as this diagram.
Yeah.
Yes.
Except it is really the same. Is that what you're telling me?
Yeah, it is the same. I'm going to actually redraw that, so it's going to be the same.
Okay.
Yeah. It's the same. It's just a kind of
Okay, I mean, again, this all really helps to make, you know, by the time it's a herd of controllers, I'm much more motivated to learn how each one works.
Yeah. Well,
how many other ones are there?
Half a dozen.
Yeah.
And so they're all star controller, is that correct?
No.
I mean, they will be.
They will be.
Why were they called gains before?
Because they were doing something a little bit simpler and they were just basically a linear gain. Because in that simple case that they solve, the controller is literally just a dot product, a linear gain.
I see. But the packaging that we will eventually have is that every one of these will return a systems model controller data.
Yeah, exactly.
Yeah, that's already do actually. When we change the name, right now you have to give an additional property to get that data, but when you change the name, the plan is to just by default return this controller data for all.
And that gives you the nice workflow.
Well, that is a much better workflow. Yes, yeah. I mean, listen, it really helps to have a herd of functions, all.
We just very limited bandwidth. We have a little bit we have very limited bandwidth, for control development. So.
Well, okay, but I think that, okay, so
coming in steps.
Okay. Well, again, this function, I mean, if you're confident of this, Roger, I just can't, I just have nothing to say. I just don't know what a quasi-feedback gains model is. I mean, I can learn all these things, but I just don't know this stuff. So now let's just look at what else you have on the agenda here. I mean, this is input-output model. What is that?
So there are two fundamental ways that you represent dynamic systems. One is a state space model and one is an input-output model.
Okay.
And an input-output model, it just uses inputs and outputs and writes the recursion equations or the differential equations in those terms. Discrete means discrete time here. And so look at that function, look at the two.
Is it the name we want to use for this? This is, this is deep inside the control systems world, but that name does not say that.
Yeah. Okay. So
I think it should say control model or something. Because
we would like, following the precedent, we would name it like discrete systems model, right?
Okay, fine.
But we wanted to actually change all systems model to input output. So that's why we are transitioning to this new name.
But I don't think that's right, because see, the problem is, by the time you name it this, our whole system is about input output, but these functions specifically aren't. They're about a feedback mechanism.
But they're not called model, the other things. So this, what we call it, state space model, right? This is input output model. Those are the two fundamental things there are.
All right.
And transfer function is just a special way of giving an input output model for linear systems.
What do you mean by input output model?
In the model, there are only inputs and outputs, and in the discrete time, previous shifts of those.
Okay. How do you see the shifts? Where are the, how do you give output at sampling instant I?
Yeah, there are examples.
I like your hand-drawn diagrams. They'll be. Yeah. They have a certain style. It's nice. Okay. In any case,
yeah, simpler examples start in scope, but this is just a summary.
So now you can see the output response. Say you feed it at an input sequence. What's the output sequence? What's the response to that input sequence?
I see. And that's representing some kind of thing with differential equations or something.
Well, difference equations in this case. So it's like sample differential equations.
Okay. So it's like, so compare this with like an Arma process.
Yeah, this is basically an Arma process.
I actually show that in properties, and you can represent an Arma using this.
Okay, but how
this one allows for nonlinear stuff. Yeah. Okay, Arma is just linear.
Yeah.
Okay, but I mean, those functions, do they have kind of a correspondence? I mean, okay, so if this was a linear function, then I could make an Arma thing out of this, right? If this was just, look, I could just make a trivial.
So here's the assumption for Arma. So for a control system, you need an Armax, Arma X. X means exogenous input.
Okay.
Like you have an ARX.
Yeah, it's an autoregressive, means it's operating on its own tail. So
yes, right. So Arma and AR and so on, they assume that you only have basically white noise driving them.
Okay.
Okay, but this one's like in control systems, you have both white noise and control driving your process.
Okay.
So
okay. So this thing, go ahead.
No, we didn't do, when we did random processes, we debated whether we should do the build out to exogenous input support as is relevant for control systems. We didn't do that. We stopped with Arma. We didn't do Armax. You know what I'm saying?
Okay.
There's a whole exogenous input family.
Okay.
This will be improved in the next version. There's a deeper, these are mild improvements.
Okay, this was the thing I was complaining about before, about caching.
Yes, correct. But there's a lot of deeper bugs being fixed and built right now. That's going to make it.
Okay, so look, just, I think it will help a lot to rename these things so we don't have all these if it's all a star controller family and so on, that's really going to help.
We will do that for 13.2.
Okay. I think also getting this workflow to really work so that and we know we need to get rid of the system model examples thing and replace that with a more generic, essentially repository browser. Right? Now, I'm just trying to understand, has any work been done on getting linguistics for these entities and so on?
No, I was going to organize that, but then you organized it, and I don't know what's then happened.
No, I didn't organize it.
You called me into some meeting about that, but then I said fine, then I'm not doing it. But we can grab a hold of it.
Yeah, you should be doing it. I mean, I offered some resources for people who know about linguistic curation. That's about it.
Okay.
Because nobody knows that. I mean, somebody, it's okay. Because I mean, I think if we can make this workflow work, I mean, unless you think this workflow is silly for some reason, but it doesn't seem silly to me. We have to work through it, and I'm sure we'll find useful
scenarios for which it works.
Yeah, I think that what will happen is there are a lot of obvious named things for which it should work. Right. Then there are things where it's a whole complicated story, right? I mean, it's also things where, if you understand the disambiguation mechanisms, you'll be able to, deal with this with just the generic ... disambiguation, okay, to deal with this case. And, I mean, what's an example? Give me an example from, system model. If I say, give me a bulldozer, okay, clearly there's a great diversity of bulldozers.
But there's a great diversity of almost everything. Like,
I know.
If you ask for an electrical motor, it's the same as asking for like a motor, like an engine. It's like there's lots of engines in the world.
Okay, so if you ask for a hamburger, okay,
yeah,
there's also lots of kinds of hamburgers.
That's true.
And so we've got a whole mechanism for dealing with, well, this is a generic hamburger because we happen to have the concept of a generic hamburger. But we have a whole mechanism for dealing with all of this stuff, right? That goes, so I suspect this particular thing, I don't know, what's another kind of food? A pie. Okay, I don't know what that's going to do. That's going to say food type. Okay, so I think these are obviously very generic food types.
How many calories in that pie?
That's a good question. I don't know. We can say
my God.
Well, the question is why it's, why it hasn't disambiguated, why there isn't more disambiguation here. I'm confused by that. Before it will give you a nutrition label, so to speak. But there may be some, who knows, there may be some world standard of I mean, I don't know,
I didn't even know that that's what I meant when I said pie. But it's interesting. That's an interesting.
It's a pretty decent model for what you're trying to do. Okay. A food type. Okay. I don't know what this is going to do here for food type. I'm surprised that this doesn't give more disambiguation immediately. But the point here is, this is the mechanism you should be using to disambiguate bulldozers and things, in my view. And there are many purposes for which sort of having the generic bulldozer is already useful. And there are other purposes for which you need to know tremendous details to do anything useful.
No, you're right. And actually, that's how the libraries kind of actually work in their own right for components and stuff.
Fine. I think you should just follow the way it's done for food. It's pretty well developed, although I'm a little disappointed that this and I don't know who's here from project management.
I'm here from project management, Kristen.
Okay, so please take a screenshot of that, send it to Michael, ask him what the heck that is.
Yes, I will.
Should take a screenshot. Okay, well, we should wrap up here. But
okay,
sorry, I couldn't be more helpful. I mean, I'm trying to.
No, I want us to sort of, I wanted to get this. Control systems is really quite simple. Control, it's like it's obvious. We all do it ourselves. We just need to.
Yes, but I claim there's smoothing of the the sort of exterior of the workflow that will dramatically help in making the thing not just seem like, oh, you have to go and study every detail of this to be able to use it. Because the thing that to me is going to be exciting is when we can take something like, just like we can take machine learning, which could be very complicated, or we can take eta reduction, let's say, which could be very complicated, and we can consumerize it to the point where you can use it even if you're not an expert on that.
Yeah.
Right? To me, this isn't to that point. Right?
No.
I could imagine.
No, it's not. We built elements of it, like PID tune is one of those consumerish things, and we're moving same of those workflows on, but there are more tails.
But right, but the question is, could we write something where, I don't know, when we are trying to do something about server configurations or something which could use control system. I'm not sure if it can, but just like can we actually use our queuing theory system to deal with stuff to do with load balancing? That hasn't been tried yet. We may have to try it, but that's the place where, as far as I'm concerned, if that works, then it's good. We've got a well usable workflow. If it doesn't work, then one's unhappy. All right, we should wrap up here.
Okay, thank you.